هذا سلامات لا وفانا سلكك أفيدة
Hey, Dr. Ra. Okay. All right, good. Thank you, Sid. All right, just Dr. Rao, I just called him in just 1 minute. He's opening his stuff. So just what the second, people are joining. So it would be good to have more people attend the lecture. Okay. So in the meantime, I think I can tell you what the day will be. So we'll start a little bit of genomics in particularly taking my own work, but in a broader sense that as most of you know, precision medicine is now becoming a reality in the West. So it's a good opportunity for us to catch it up now. So especially being Ethiopia as a center of, diversity and origin, the more we study the Ethiopian population in terms of genomics, the more we can find a cure for a lot of diseases based on genomics. So one of the challenge, or I think one of the opportunity I would say is, there's not much study so far, but it's an opportunity to launch each of you in each of the institution that you are running. Consider opening human genomics. That is the future. So a new area that can really capitalize all other investment, not just for the sake of human genetics. It leads to a lot of development in many areas. The technology is really rapidly changing in a big way. So I really encourage anyone interested in a university to start human genetics program, and then move further to, studying the diversity, the geographic or ethnic diversity in terms using genomic markers rather than, historical, self-reported kind of character. So how people related to each other, geographically, ethnically, or globally. So studying the Ethiopian population really gives a more diverse picture. What we study now is the Western European. Wait me a second. Hello.
Hello.
The link will be the same as what you have yesterday, but I also sent you.
Yes.
Okay, I'll send you now.
Yes.
Wait me a second and go. Okay. I just sent you, Dr. Rao. Check your email. Check it if there is any problem with that. Uh-huh. All right, guys, sorry. Dr. Rao has some problem with connection. So he's now on. Are you there? Okay, good to see you. Good morning. Dr. Rao, you are muted. All
Okay,
right.
can you see me now? Can you hear
Yes.
me?
Yes. Thank you. Good
Yeah.
morning.
Yeah. Okay, let me.
I was starting, just give me 5-10 minutes. I was telling them about genomics.
Okay, that's good. You go ahead.
Yeah.
Meanwhile, I'll start loading things.
Yes, that would be good.
Okay.
Okay, let me share the program first and then we'll go from there. All right. Again, good afternoon. Thank you everyone for coming. I know there is a lot of things to do. Thank you for choosing to join this workshop. So as I mentioned earlier, today will be day 2, and in day 2 we will cover the following. I'll give you a little, just 10 minutes of, in relation to data science, the field of genomics and epidemiology, where we are now. And you always need to link this to what you are going to learn in R. So this in that context. So, but I think that the main topic for today would be this, taking regression and categorical variables on the outcome variable is categorical. But the most important thing that Dr. Rao mentioned is that this is really important if someone is interested to join the next session, which is more advanced data mining, machine learning, and deep learning, and all those artificial intelligence. So this is the foundation. So he will cover this logistic, multinomial, ordinal regression with, as you know, like from yesterday, it's more hands-on, and you feel it when you do it. So that's going to happen today. So put your question in the chat box, and we'll have discussion in the end. So let me open now just a few slides so that can to give you more perspective of the field of genomics from the data science point of view. So let me put it this. Okay, so as you probably know, Dr. Rao and me are just actually a few meters apart. So he's in the next building, I'm in this building. So we usually see each other once every other day or sometimes for meetings. But because of pandemics, I think it has been over a year since we see each other in person. In any case, it's in Cincinnati, Ohio, just somewhere in the Midwest. So what's big data in genomics? So, and where it comes from? So as you start from high school or undergraduate or college level, we learn to understand genomics, just genomics, not actually genomics, genetics. It's just few genes or variant at SNP level or at the microsatellite level, actually. So now all this what you see, you know, transcriptome, proteome, metabolome, microbiome, epigenome, and of course, including the exposome, actually exposure to the environmental exposure. All these are really becoming part of the whole enterprise of human genomics, or you can say human studies. And now on top of that, we have this social media, so data from Twitter, Facebook, and all other, bioimaging, infrared and biosensors. So all this data is we're collecting every hour, every day. So imagine the billions of data points you have just from a single person. So you have from you, we take a blood sample and we can generate all this data. The problem is not generating this data. We can generate this in my own institution, all this at a time. The problem is how to analyze and how to interpret. So that comes the data science idea, and the errors is the main livelihood for this area. So in my own lifetime, we used to have this big, disk with a kilobyte data. Now we can have as big as Zeta, and you cannot even carry it it had to be stored in a cloud, and it's not manageable even an individual personal computer level. So the iPhone is now actually much bigger than the personal computer. So you can see how things are moving rapidly for the last 10, 20 years. So in human genomics, we call it multi-omics, and those data are coming from different sources. So we have this 1,000 genome, over 100 million genetic variant data points. In the past, we have HapMap, and from Wellcome Trust, we have all this, the UK Biobank. dbGaP is another data set, and GTX, gene expression. All these are, most of them are publicly available. So you as a young person with computational skill, you can actually go and access this data for free. You can publish, you can analyze, you can present it. So it's not the time you need to generate all this by yourself. The data is freely available in the public domain. So I think that's really good, especially for junior people that they don't know where to get the data. These are freely available data. You just download, and of course, downloading and analyzing billions of data points is not an easy, but if you have the opportunity to do that, the data is already there. So if you look at the human genetics over the last 20 years, I was a graduate student in 2000. So at that point, number of markers is about 26 across the whole genome. Across the 23 chromosome, there were 26 markers with only 800 samples. These are really very limited number of sample and markers, molecular markers. Now we can see that right now at the moment, after 20 plus years, over 1 billion marker. And of course, the sample is going up, but it's now across over 500,000. So you can imagine how things shift rapidly over the last 20 years. And now, not only having big data, this data is in most cases freely available. Anyone with expertise and interest can analyze and publish without any restriction. So, and the other point is, how do you integrate? This is actually the challenge point that I want to mention. So you as a computational bioinformatics, system biology, or computational biology, there are different names, but you have this clinical data from different sources, environmental factor. These are the multi-omics thing, the epigenome, the microbiome, the proteome. But the problem is they are supporting each other. They are not really, overlapping each other. There is they are complementary in most sense. So what you need is like a person to develop some machine learning algorithm. How do you interpret this data? I mean, analyze the data in a more unified way, and of course, lead to some precision medicine. This is type of thing. Instead of giving medication, the same medication to everybody, how do you stratify patients based on their profile, molecular profile? So that is, one thing is good because everybody got the right drug, the right time, the right dose. The problem is, how do we get this box? So that's the challenge. I would say this is also a big opportunity for you to think of in terms of multi-omics study. And also in exposure data and epidemiology, there are a lot of exposure data from traffic pollution to environmental degradation. All this exposure you can measure against the molecular multi-omics data. Of course, you need again machine learning and then interpret through your outcome, which is the interest, like the outcome of interest. It could be asthma in my case, or anything that you are interested in. In my lab, we do all this exposure, environmental exposure, overlay with genetic data, and outcome. In most cases, we do asthma, but we also do other things. But this is how you use statistical knowledge inference to link your exposure to outcome. In this case, allergies. So I think there are tells and truths in analysis. In some cases, people think there's one best design to answer each question or research question. And we always think to have the best or the gold standard of randomized or controlled research trials. And in some cases, we always think descriptive analysis studies are useless. And there are things that we can achieve perfection when conducting research. So the truth is, there are often many ways to approach the same question. I showed you multi-omics data. The analysis actually is very different if you approach it from different sides. So there is multiple ways you can develop methods. I'm encouraging you to develop methods. You don't need to follow all the methods that's out there. There are positives and negative side of each design or your methods. You should upfront mention those problems and challenges and opportunities, and of course, there are decisions that should limit some of the things that you are planning to in terms of the realities of resource and other things. So the final point is all research design have potential, strengths, and limitations. So as I mentioned, this is my last point, my last slide, I believe. As I mentioned, we have all these different multi-omics data. As I mentioned, metabolomics, proteomics, metallomics, RNA-seq or whole genome sequencing. So as you can see, they are by themselves, they are high dimensional. At the same time, they are not independent, they are interacting. So you can see this equatorial, all these different interactions. So the challenge is, at one time, on one hand, they are very high dimensional, they are big, and the other things are not independent. So how do you deal all this complicated statistical modeling of this kind of data? Of course, the advantages at the end, the clinical implication is very, very promising, but this is the challenge that we always need to face. So, but I feel this is an opportunity for young people like you to deal. So the home take message, I think we need to look at your data, what kind of data you have in terms of epidemiologic outcomes or variables. Do you have nominal, interval, ratio, or real data? And once you have the right data, the right analysis, the final thing for you is let the data speak themselves, because eventually what we need is repeatability, and the data has to be repeated by an independent investigator. So I think Dr. Rao will take some of these data types and continue the discussion. All right, I'll stop here and leave for Dr. Rao to start with the variable type and data analysis. Thank you very much.
Thanks very much. Yes. Okay.
Yes.
This is a kind of a panoramic introduction to big
Yes,
data.
that's
That's wonderfully laid out, and this talk could go anywhere, okay, for any group. Okay. So what I want to do, I sent notes for day 2. This is about categorical regression. And I'll also talk about some issues, how to download the data from R, things like that. Okay. So first of all, let me share some documents. Okay. So let us see, share screen. I'm going to click on that. And the first thing I would like to share is my notes. So highlight it and click share. I hope you can see it.
Yes, we see it.
Okay. And I want to share another thing as well. So let me, okay, new share, click on that. And then I like to share my R console. Highlight it and click share. So you can see my R console along with the R editor. Good.
Yes, we don't
then
see
I
you.
want to share one more things. I committed a mistake. I should have sent the data to you guys to begin with. But anyway, I'll send the data to Tess. He will forward the data to you. So let me.
We don't see, Dr. Rao, we don't see your notes. If you want it, we don't see your note.
Oh, you don't see the R console?
We see that. We don't see your handout. If you want to see.
Handout will come on. I mean, it is there in the background.
Okay, good.
Whenever it is needed, I'll bring it in.
All right, thanks.
Okay, and I'm sharing a new data. This is my sepsis data. Highlight it and click share. Can you see the data here?
Yes.
Okay, very good. Let me bring my notes forward. Can you see the notes now?
No, we don't see it.
You can't see it. Okay.
Maybe, if you share the screen like you did yesterday, it can show, you can minimize and expand whenever you want. Now we only see the Excel spreadsheet.
You only see the Excel. Okay.
Maybe.
Well, I'm trying to share 3 things: notes, Excel sheet, and R console. And they're all there in the background. Let me see.
So why don't you ensure and share the screen, the entire screen, so that you can select whichever file you want.
Okay. share the entire screen?
Yeah, first maybe unsure this one, and
Okay.
like you did yesterday.
Okay. How do I share the entire screen? Is there what should I click on?
Uh,
Let me try again. So it is showing only one at a time.
the other one could be minimized, you know.
Try to minimize this one. I did that. On my screen, I see R, console, and the editor.
No, we only see, at least I see only the Excel. So why don't you unsure this one? Unsure right now you can unsure or stop
Okay.
sharing.
Okay.
Stop
All
sharing.
right, go ahead. Yeah.
Stop sharing, and then when you click share, you can, there is the entire screen.
Okay. Our screen sharing is paused. Okay. Okay.
Unsure this one first. I mean,
Okay.
stop sharing.
Okay. Oh, first stop share. Okay.
Yeah.
I did that.
Yeah. And then I think there's if you look at share, and then there is a one box which says screen.
Okay. I mean, you want me to click on share screen?
Yeah, and then you'll see the rest of the file minimized down there. You can just
Okay. And you know, the things are coming up. Okay. I can only, when you say share, I can only do it one at a time.
not particular file. When you say share, don't click one file. Otherwise, you will only see that file. If you share the screen, you're showing us all what you have, and you can switch from one file to the other.
Okay, let me see. Okay, let me see. I don't know, just entire screen. Okay. I don't know, just 1 minute. I'm always getting into trouble with Zoom. Yeah.
We'll get there.
Yeah. So I.
Now we see your R.
R, and then I want to show my notes as well. Let me see. You don't see the. Do you see the notes now?
No.
No.
We'll only see the R.
Okay. But at the top, right. Shall I click on new share?
Yeah.
I'm clicking on new share, and then I click on my notes. I'm clicking on my notes. Okay. And then share.
Yes, we see your note now.
Yeah, but you know, can you see R as well?
No, because I think if you share the screen without selecting any file.
Share the screen without let's stop sharing then.
Yeah.
And share screen just blank.
Yeah.
But you know, something gets highlighted here. That's the problem.
The highlight the blank one.
Highlight the black. Oh, yeah. Okay. Now I'll do share.
Yeah. Now
Yes,
you can
now
switch from.
yeah.
Okay. Now you see my notes.
Yes, we see your note. If you go to R, we should see yeah. Now we see your R. You can switch from one to other one.
Okay, one to the other. You can see my data as well.
Yes. Now we see all you are just seeing your screen.
Okay. So okay. All right.
Very good.
So okay, let me see. Let me go to my notes. Okay, all right. I'm ready. I'm poised.
Very good. Thank you.
Okay. Okay. You know, there are few things with R. One is the fundamental question is, I have my data in Excel format. How do I download the data into R? This is one of the basic questions. There are 10,000 packages, more than 10,000 packages in R. Each package is tailored to tackle one statistical problem, maybe a few statistical problems, a few statistical data analysis problems. Okay. Do we need all these packages? No. A few packages are good enough, some basic analysis. Okay. I will come to that little later. Okay. And another thing is, today I want to start something, an important topic is called a regression when the outcome variable is categorical. Sometimes I call outcome variable as response variable. Okay. People are used to response variables which are quantitative, numeric. But now I'm looking at a response variable which is a categorical. Okay. It's a multi-level response. You know, if you look at this kind of a regression, this is at the core of a pattern recognition, machine learning, neural networks, face recognition, text analysis, deep learning, and artificial intelligence. This is something basic. Whatever you want to learn neural networks, they say that they start with what you call logistic regression. You want to do some text analysis, some deep learning problems, then they want you to learn about logistic regression, multinomial regression, and ordinal regression. Okay. So there are three topics I'm going to cover as much as possible today, if not by the end of next day. Today, I'm going to focus on logistic regression. I'm talking about a binary response variable, a binary outcome variable. The word binary means two levels. A variable with only two possible outcomes. The focus now is developing a regression model whose outcome variable is binary, two groups or patterns. In multiple regression, the response variable is numeric or quantitative. I want you to distinguish between a categorical response variable and a numeric response variable. Okay. There is a lot of papers, many textbooks deal with multiple regression. Simple linear regression we have already seen yesterday, and you can extend it to multiple regression in the sense we have not one predictor, many predictors. Okay. I always start with a new notion with an example. So let me talk about a particular data set. A patient is admitted with abdominal sepsis. Okay. Another name is blood poisoning. The case is severe. You know, the blood is poisoned. You need to pump out the blood, entire blood, and put in new blood. Surgery is urgent. So the case is severe enough to warrant surgery. So the patient is wheeled to the operation theater, and let us speculate what will happen after the surgery. I'm going to introduce a variable. Why? What could happen after surgery? What are they looking at? Looking at is 30-day mortality. Y equal to 1 if death follows within 30 days after surgery. You can say that the surgery was a failure and equal to 0 otherwise. Okay. So the outcome Y is binary. Either that happens or this happens. And can anybody say definitively what exactly will happen after surgery? No. That's why I say that the outcome is random. Since it is random, we want to know its probability distribution. This means we want to know what are the chances death follows within 30 days after surgery. Call it, given a symbol, call it as a pi. And what are the chances he survives? Okay, call that probability as 1 minus pi. This is what I meant by probability distribution of the outcome. Either y equal to 1 or y equal to 0. Either death follows or survival occurs. Either this or that. So when you talk about the probabilities must add up to 1. They must be non-negative and must add up to 1. That's why I wrote symbolically pi and 1 minus pi. So you can see that they add up to 1. In simplistic terms, we want to know the chances that a patient dies after surgery. Equivalently, what are the chances of survival after surgery? Okay. If it is such a plain question, yeah, maybe can data allow you to estimate the chances? But are there any prognostic variables or factors which could influence the outcome of Y? Are there some predictors? Are there some factors? So the probability of death or the probability of a survival depends on these factors. And the surgeons list the following variables which could have some bearing on Y. They say that surgeons say that the survival or death depends on number of factors. They identified these 5 factors. Okay, the patient is wheeled in, easy in a shop. Okay, yes or no? And is the patient undernourished? Yes or no? Is the patient alcoholic? Yes or no? What is the patient's age? You can find out. And has the patient bowel infarction before in the past? Yes or no? So the surgeons believe that the chances of survival or the chances of death after surgery depends on this, possibly could depend on the 5 factors. The question is, how do I model the death probability as a function of these 5 covariates? This is a modeling problem. Okay. If you look at these variables, they're categorical. There are 4 of them are categorical. The predictors, I'm talking about shock, undernourishment, alcoholism, and bowel infarction, they're all categorical. Not only categorical, they're all binary. Either this or that. The only numeric variable in the list is the age. Age could be anything. So it is a numeric. Okay. It is felt that the outcome Y or pi depends on this covariate. You can call them covariates or predictors. You can call them as independent variables. So many different names you have. Okay. So let me make a list. My response variable is Y, which is binary, either death or survival. And the covariates, predictors, independent variables, effects, there are so many different names. Okay. How do I model Y in terms of the predictor? If Y is numeric, I can do it. You can do what is called a multiple regression model. But Y is not numeric. It's a binary, categorical, death or survival. How do I model Y in terms of predictors? I'm not modeling Y directly in terms of the predictors. I'm modeling the distribution of Y in terms of the prediction. I'm trying to model the probability of death as a function of the COVID. You know, I have data. The data came to me, or I gathered the data from Ohio State University. Okay. And I have a data on 106 patients, right? So you look at it, say, I want to tell you the structure of the data. Look at a patient number 1. X1 equal to 1. He was in shock. X2 is equal to 1. He is undernourished. X3 equal to 1. He is alcoholic. And X5 equal to 1. He had a bowel infarction in the past. And X4 is equal to age, is 47 years old. What happened to him after surgery? Y equal to 1, he died. Okay. And you know, this particular patient, many things wrong. He was in shock, he's undernourished, he was alcoholic, he had a bowel infarction, he's not a spring chicken. A middle-aged guy, 47 years of age. And of surgery, what happened to him? He died. On the other hand, look at patient number 3. X1 equal to 0, he's not in shock. X2 is equal to 1, he is undernourished. X3 is equal to 0, he is not alcoholic. X5 equal to 0, he did not have a bowel infarction. And his age is 32 years. I would say pretty young. What happened to him after surgery? Y equal to 0. He survived. I can say patient number 3 has good habits. Not alcoholic, not in shock, did not have a bowel infarction. On top of that, is pretty young. Okay, what happened to the outcome? He survived. So we have this kind of responses and the predictors. I want to see patterns. I want to explore the connection between the response and the predictors. You know, this data is very, very well laid out, and you can learn a lot from analyzing this data. I can use the data from a variety of contexts. I can use what you call data mining techniques on this data and extract some signals. Okay, we will enjoy the data. We have data on 106 patients. Okay, data came from the medical hospital attached to Ohio State University. The entire data is an Excel folder under the name sepsis. I hope, I'm requesting tests to provide you access to this data. Okay. All right. Let us look at the data on R. Okay. And what happens, you know, if you have Windows, one can download the Excel folder into R console. Just copy the data to your clipboard. The R function is read.dlim. If you have a Mac, downloading the data into R is a little tricky. Go to internet for help. Okay. So what I'm going to do, I have Windows here, and I want to show you how to download the data. What I'm going to show is I will show you the data what I have. I hope you can see the data.
Yes,
Okay?
yes, we see it.
Data. My
Yes.
data is an Excel folder. And I have how many? 6 variables or 6 columns. The first column gives information on shock. 0 or 1. 1 means shock, 0 means not in shock. And you have a malnutrition, 0 or 1. Alcoholism, 0 or 1. Age is a numeric. Infarction, 0 or 1. Outcome, 1 means death, 0 means survival. This is Excel data. How do I download this data into R? I'm on Windows. So what I do, copy the data, highlight it. No, not that one. Sorry. Not from here. Okay. Highlight the data. Entire data is highlighted. And I have an icon here, copy. Click on copy. So you know the border is forming. And then I go to my R console. And I go to editor. Give a name. Call the data sepsis. Whatever name you give, you can type it up. R function is read dot delim. That's an R function. Parentheses, double quotes. Okay. The data is copied to the clipboard. Just type clipboard. That's it. So the data in the clipboard is read by R. The whole data is in the folder I created called sepsis. And there are 5 icons on the left side in R console. Go to the middle one and click on it. The data is loaded. So the data is loaded into R console. And typically I do some basic things. Okay. I want to know how big is the data. The R function for that is dim. Dim is an acronym for dimension. What is the dimension of the data? Sepsis. My data now is called sepsis. What is the dimension of the data? And go to the middle icon here. Click on it. 106 rows and 6 columns. Okay. You know, if you want to look at the entire data, you simply type sepsis. It will show up the entire data. I don't want to do that. I want to look at the top 6 rows. So the R function for that is a head. Show me the top 6 rows. Head of sepsis. Show me the top 6 rows. And click on the middle icon. This is it. The first guy is not in shock. He doesn't have a malnutrition. He's not alcoholic. His age is 56 years. He did not have infarction in the past. What happened to him? He survived. Look at the 6th guy in the data. He's not in shock. He's malnourished and is not alcoholic. Good, but 87 years of age. Okay, and pretty advanced age, and he has no infarction in the past. You know, seem to have all good habits except undernourishment. But what happened to me after surgery? He died. Maybe age is playing a role. So looking at this bunch of data, this kind of a data, we want to pinpoint what led him to his death. In this case, it seems to be age. How can you enshrine this kind of things you gather, something concrete, something as a mathematical model? That's the purpose. Okay. Maybe some good habits lead to outcome, good outcome. Maybe a couple of bad habits might lead to a bad outcome. Okay. Intuitively speaking. All right. There is another interesting R function called tail.
There's a question, Dr. Rao. There's a question. Can you send me by email? We can share the data.
Okay. So I can forward it by email to you.
Yeah, I can send to them.
Yeah,
attach them.
it's a good idea. They should have that hands on the data.
Yeah,
Okay.
there are some.
Okay, let me see. Let me see. Okay, I had to do something. Okay, new window, and I had to go to my email. Okay. Okay. And let me see, Marsha. Okay. And can I say reply somewhere? Let me see. Reply.
Yeah.
Okay. And then I would like to say, here is the data.
Very good.
Okay. And I have to attach.
Attach. Yeah.
Attach. I think maybe I have to browse. Okay, let me browse it. Let me see. Add an account recent Peterson fan wedding Bhupati. How do I get to? Let me see. I have this one. Will it get attached? I'm not sure.
Yeah.
Huh?
Why don't you save this in a desktop? You can save this one in the desktop and you can find it easily.
Why don't you? What should I do again? Okay. Let me do one thing. Let me go to. Okay. Let me see. Since I have data here.
Okay.
Okay.
You can copy and then paste there.
Okay. And I have this data. I should copy this one.
You can copy and paste in the it's no big data. You can copy the data. I can put it in Excel. Yeah, you can copy that, the entire data.
Copy this is already in Excel.
Yeah, just copy that and paste in the email.
Okay. Okay, let me see. Trying to go back to my email. Okay. See my email, I'm not sure. Okay. So I'm back to Marsha.
Yeah.
Okay, I already here is the data, and I need to. Oh, things have disappeared.
Click the first one, the top one. Yeah.
The top one, delete.
No, the draft. It says the draft. Down the email, in the email. Yeah, down.
Down.
Down then.
Okay, so this message has not been sent.
Yeah. Click that one.
Okay,
the
click
draft on the right on the.
Okay. And workshop, Gondar, etc.
No, not that one.
Okay.
If you go.
So let me try again.
Yeah.
Overview, email, chat, catering, professor, organization. Should I? Email.
Yeah.
Okay. This Ohio meeting Sharp midterm solutions.
Now I think you may need to cancel this one and go to the, yeah.
Go to email again.
The email, yeah, cancel it on the right side, yeah. On the right top, yeah.
I have to close it then.
Yeah, close it and you go back to the
Yeah.
email.
Yeah, I went back to email, but all those icons are missing.
You see the three dots down here is the data.
Yeah. Right,
Click
right.
there. Yeah. Now you can post it. Now click the three dots again. It's not open yet. The three dots.
3 dots again. Okay.
Yeah.
And I click it again.
Yeah, I don't see the.
I don't see all those icons are missing.
He can send it in any new message again.
Yeah, send us a new.
A new message.
Okay, just abandon this one.
Yeah.
Okay, let us see. Okay.
New message on the top left.
Top left, new message.
New message, yeah. Type the Marsha, you may get it there. Yeah, the first one.
First one.
And then paste it down, go down the text box, okay. Yeah.
And let us
Yeah.
I'm just at what's the subject.
Okay. And then paste the data there.
Okay, let me see. Here is the data. Okay. And attach.
Yeah, enter and attach. Enter. No, you need to paste it. You already copied it. Copy in your.
Oh, I see.
Enter and then paste there.
Control V.
Yeah.
Control V. Oh, it's here.
Yeah. So I'm sure it's the entire data, and click send on the top. Then I will put it in Excel.
Okay. Hope. Did you get it?
Let me check.
Okay.
Yeah, I should come. You can go back to.
Okay. All right. Just 1 minute. You should come in due time. Yeah. Okay. So what I will do, I'll just.
Sorry, interrupting you on this.
No, that's okay. Something is minimized. Okay.
Yeah, I have the data.
You have the data. Very good. Good news.
Yeah. I'll send them. Yeah.
Okay.
Yeah,
So,
you can minimize this and you go to.
let me see. And I had to. How do I?
You can minimize that. The one. Yeah.
But I need to get the screen back.
Yeah. If you go down, you'll see what you're on the R or which one. If you go to the right,
I can be in R.
Yeah, go to the right of the cursor.
Okay.
Yeah. Yes, we see your R now.
You can see. Oh, that's good. At last, success on the plate.
Yes, thank you.
Okay, you got the data. Very good.
Yeah.
And I want to show you another R function called sepsis. Okay. What it does, the tail means show me the bottom 6 rows. That's what it means. Okay. And click on it. I got it. 101st guy, 102nd guy, 3rd, 4th, 5th, and 6th. I showed you the top 6 rows and the bottom 6 rows. Okay. So we have the data, and I try to understand. It's called the data domain. Okay. So there is a phrase called the data domain. understand the data. Okay. For a successful analysis, understand the data. Okay, all right. Now I haven't spoken about the modeling. How do I model the outcome in terms of these 5 predictors? I need to talk a little bit about it. So let me go back to my notes. You can see the notes. Is that okay?
Yes, yes, we see it.
Very good. Very good.
Mm.
A fundamental question is how to quantify the connection between the predictors and the outcome. This is the modeling exercise. Does shock have an impact on death? Do death and shock are significantly associated? How prediction is carried out? How the classification protocol stems from this model? You know, some people do some kind of a very simple analysis. Okay, we can do some simple analysis too. Okay, and let me go back to my R console. Okay, simple analysis means you can choose one of the predictors, like a shock, alcoholism, or and the outcome variable. So people ask me, do you think a shock and outcome are connected? Okay, how do I answer that kind of a question? Okay. Do shock and outcome of surgery, okay, associated and that is some kind of an, I will say, is a naive analysis. How do I do that naive analysis? Okay. So cross tabulate and a shock and outcome. Okay, and I want to show you a very useful function in the data analysis. The function is called table. Okay, and what you can do, you go to sepsis, that's a mother folder, dollar, the daughter is white outcome. You go to the outcome variable. You have to identify the mother, otherwise R will not recognize. R knows sepsis. R doesn't know the daughters. All the 6 columns it doesn't know unless you tell R, go to sepsis and pick up outcome. Okay, and the sepsis dollar shock. When I say cross tabulation, what does it mean? Look at shock is binary, 0 or 1. Outcome is binary, 0 or 1. Cross tabulation means how many 0 zeros, how many 0 ones, how many 1 zeros, and how many 1 ones. A 0 of shock and a 0 of outcome. How many? A 0 of shock, outcome equal to 1. How many? Shock is equal to 1, outcome is 0. How many? Shock is equal to 1, outcome is equal to 1. How many? This is called a cross tabulation. So let us cross tabulate these 2 columns of data. Click on it. You see that. You see the outcome. How do you read it? You know, I mentioned outcome first in the command here, and the shock is equal to second. The rows are outcomes and the columns are shock. How do you read? There are 82 people or 82 subjects in the data. Outcome is equal to 0 and shock is equal to 0. And there are 3 subjects in this study. Outcome is equal to 0, shock is equal to 1. There are 14 people in the study. Outcome is equal to 1 and shock is equal to 0. And finally, there are 7 people in the study. Outcome is equal to 1 and shock is equal. This is what I call, what I get here is a 2 cross 2. This is an example of a 2 cross 2, 2 rows and 2 columns contingency table. Okay. Cross tabulation leads to a contingency table. And we get quite a bit of information. Let me write it down. Rows represent outcome. Okay. And the columns represent shock. To understand the format, I can say something more. Okay. And there are 85 subjects in the study. There are 85 subjects in the study who survived, because 82 plus 3, 85. All of them have one characteristic feature, namely 0. Outcome is equal to 0. They survive. Okay. And then you can also say there are 21 subjects in the study who died. Because 14 plus 7, all of these guys have outcome equal to 1. Therefore, 21 subjects have outcome equal to 1, which means death. Okay. Who died. Okay. Now, what can I say about this data? I can do something very simple. What are the chances of death given that the subject is not in shock? Okay. And how do I answer this question? The subject is not in shock. How many subjects are not in shock? You look at the column. The first column, 0 means not in shock. The second column, 1 means in shock. So how many people you're not in shock? You're talking about 96. Out of 96 people not in shock, how many died? 40. Okay. This is called a conditional probability. And we are talking about 14 divided by 96. And they can just run it. 14% or 14.5%. Or you can say the answer is, okay, 14.6%. Okay. And on the other hand, I can ask the following question. Okay. What are the chances, probability of death, conditional probability, given that the patient is in shock? Okay. How many people are in shock? 10. Out of 10 people, how many died? 7. 7 over 10, and that is equal to 70%. Okay. People start asking, if a patient is in shock, looking at the data, what are the chances of dying? 70%. If he is not in shock, looking at the data, what are the chances of death? 14.6%. You can see a big gap. Okay, there is a big gap. Okay, there is a big gap. 14.6% versus 70%. And as a statistician, we always ask the question, is the difference significant? Okay, is the difference significant? Okay, I mean, to my naked eye, yes, there is a big difference. But statistical point of view, is the difference significant? Okay, and how do you answer this question? Conduct a chi-square test. Conduct a chi-square test. So I have to go back to the table. Okay. So what I do, chi-square, the function is chi-square dot test. Apply to the table. I should have given a name. Otherwise, I have to type the whole thing. Okay. Let me see. I should have given a name. Things might have simplified. Maybe it's not even too late. So what I do, let me see, call this table as MB. Okay, run it. You get the same thing. Okay? I'm giving a name, so it is easy for future reference. You got the same thing. So you can do chi-square dot test MB, apply to the data in MB. Okay, and that's it. Pearson's chi-square test with the Yates continuity correction, etc. What you need to look at is the p-value. You look at the p-value, and that happens to be 0.000165, and is much, much less than 0.05, the industry standard. Okay, and you can say that. Okay, and the result, whatever you are calling the difference, is very, very significant. Result is very, very significant. It's less than 0.001. Okay, it's very, very significant. And the people argue, okay, and we can say that shock and outcome are very, very strongly associated. They are very, very strongly associated. And all right, can you tell me a little bit more about it? Yes. And okay, if you are in shock, blood poisoning, if you are in shock, death is much more likely than survival. Okay, you are comparing shock, not in shock. So you look at two candidates. One is in shock, the other one is not in shock. Who is more likely to die? The guy is in shock. How much more likely? Is 14.6% versus 70%. That's how you answer the question. A layman interpretation. Okay. So it's such a simple, naive analysis you can do. You take the outcome variable, you take any one of the predictors, and start asking questions like this. And a caveat. This analysis ignores other predictors. Because what I did, I studied shock and outcome in isolation. What about the presence of other predictors? I just ignored it. Okay? But a real analyst to find a way to bring the other predictors into fold. That's what I wanted to talk about it. You know, this analysis also could be done when you write a paper. Typically, the editor asks you, you do this kind of a piecemeal analysis, pair by pair. Okay, talk about the outcome versus shock, outcome versus alcoholism, outcome versus infarction, and you can also study the connection between outcome and age. Okay, so you can do, you have to do all these piecemeal analysis. Look at this one. Okay, and outcome versus shock, outcome versus malnutrition, outcome versus alcoholism, outcome versus infarction. You can build a two cross two tables. You can prepare a table and include that table in the paper. But they will also ask, what is the connection between age and outcome in isolation? How do I do that? Age is not categorical, it's a numeric. How do I study the connection between age and outcome? Intuitively, I feel the older you are, the more likely you die. But how do I say it statistically? What I can do here, if you are familiar, we can do two sample t-tests. Look at outcome 0. Look at the ages. Look at outcome 1 and look at the ages. It's a two sample problem. Okay, you conduct a two sample t-test, and if you reject it, you can say that, outcome and age are connected. Outcome and age are associated. Okay, these are all simple things. These are all simple things, and you need to do these things if you are writing a paper. Okay, let me go back to my notes and let me talk about the models. Okay, chi-square test. Okay, here, further thoughts. Death and shock are two binary variables. How do you measure the degree of association? And the correlation is a measure of association between two numeric variables. Is there something similar between two binary variables? How do you measure precisely association? The chi-square test statistical independence of categorical variables. It does not tell us how much they are away from independence, how much they are associated. Can you calculate the Pearson's correlation for binary variables? Typically, Pearson's correlation is reserved for bivariate data with both X and Y numeric. The odds ratio is used to measure degree of association between binary. I'm trying to bring in the concept called odds ratio. What is the correlation between two numeric variables? It is odds ratio between two binary variables. Okay. There are so many things to be done, but I want to go ahead with the model building, logistic regression. Okay. All right. Recall probability of death. Y equal to 1 means probability of death, and call it as a pi. We want to model pi as a function of x1 through x5. So in order to indicate the dependence, we write pi as a function of x1, x2, x3. Why one wants to build a model? There are many things. If a model is in place, one could use the model to assess the chances of survival after surgery for a patient before he's wheeled into the operation theater. So if you know the precise function, take a patient. You would have the information on x1, x2, x3, x4, x5. If this function is available explicitly, you plug in this information, you would know what are the chances of that. Okay. Do you want that? Just to go ahead and do surgery. They will do surgery. It's not a problem. But it's good to know, statistically speaking, what are the chances. Okay. And the family has to know also. Well, this man is a 90 years old. He had a blood poisoning. And the family has to be told, okay, we will do surgery. And what are the chances of survival? What are the chances of the family is brought into decision making. So this country is moving towards the direction. You have a medical condition and you want to find a cure, and you lay out all the options in front of the family. And then do your best. All right. Okay. And can I model the probability as a linear function of the predictors plus intercept? You can't do that. It's like a multiple regression model. On the left hand side is a probability between 0 and 1. On the right hand side could be anything. Even if you know all the betas, all the x's, there is no guarantee this will be between 0 and 1. This kind of a model is not acceptable. And some people might ask, I codified y as 0 or 1. Why don't you model y directly as a function of the covariates in the style of the linear model? I can't do it. Y takes only two values, 0 or 1, and this right hand side could be anything. You cannot force it to have the values 0 and 1. So this is not acceptable. And the model is postulated. Okay. You want to write the probability of death as a function of the covariates. So this is the function. Exponential, the power, a linear function of the covariates plus intercept, whole divided by 1 plus the same thing, exponential to the power, a linear function of the covariates plus intercept. This model looks very formidable. My goodness. how complicated it is. Okay. And, the problem is a probability on the left-hand side. You need something on the right-hand side is also between 0 and 1. Exponential of anything is positive. Whole divided by 1 plus a positive number. Therefore, the ratio is positive. And the denominator is more than the numerator. The denominator is larger than the numerator. Therefore, the ratio is less than 1. So whatever may be x1, x2, x3, x4, x5, whatever may be these parameters, beta 0, beta 1 are, you can always find the ratio between 0 and 1. That's good. Because the probability is always between 0 and 1. There is a matchup. And this is what is logistic regression model. People tried so many different ways to model this probability of a death as a function of the covariates. There are so many models out in the market. One of the earliest models was a probit model developed by the British. They have been using it for many, many, many decades. And when this logistic regression model came into picture, it became very popular, like a Cox model. Okay. It's commonly used, logistic regression model commonly used in machine learning, and then data mining, artificial intelligence, deep learning, neural networks. So this is pretty common. Okay. So get used to it. The model has 6 unknown parameters. We need to know the values of these parameters before it can be used. We can estimate the parameters of the model if we have a data on a sample of patients. We do have data. We have data on 106 patients. Using the data, can you estimate what the betas are? Okay. The approach I presented here is purely statistical. Okay. Identify the variables of interest, designate the response variable or dependent variable, and designate the covariates or independent variables, postulate a model like that, fit the model, and check its goodness. Okay. This is about how the model is fitted. This is just mathematical, technical, don't worry about it. And this is the full model. Probability of a death after surgery for a patient with the covariate values x1, x2, x3, x4, x5. And you might ask me, we are modeling the probability of a death. What about the probability of survival? Oh, that is simple. It's 1 minus of that. Okay. Probability of survival. So you can find explicitly the formula for survival. This is the probability of a death. Such a complicated expression divided by 1 plus the same complicated expression. And this is the probability of a survival, 1 over 1 plus the same complicated expression. We can check this plus that equal to 1. Good? Yeah. I want to talk about odds. Odds of death versus survival after surgery. This is the probability of a death in the numerator divided by the probability of a survival in the denominator. It's called odds of death versus survival. And it nicely simplifies an exponential of a linear function of these predictors plus intercept. And you want to get rid of exponential, take natural logarithm. Logarithm of the ratio. Log odds is also called a logit, and which is a linear function of the covariates plus intercept. This is like a multiple regression model. So you can say that the log odds are a linear function of the covariates. This form of the model is very useful for interpretation. The parameter beta 0 is called the intercept of the model. The parameter beta 1 is called the regression coefficient associated with the variable shock. The parameter beta 2 is called the regression coefficient associated with the variable malnutrition. So these regression coefficients indicate how much impact the corresponding covariates have on the response. Now people ask me, how do you measure the connection between shock and outcome? How do you measure the connection between alcoholism and outcome? If somebody asks me to quantify it, I throw this regression coefficient at them. Beta 1 measures the impact of shock on the outcome. And beta 3 measures the impact of alcoholism on the outcome. Okay, this is what I call quantification of the relationship. Okay, so you are becoming a bit technical now. Okay, so the logistic regression model can be spelled out either in this form or in the form log odds. Both are equivalent. Now what I want to do is I want to fit the model. Okay, let me go to my R console. So fit the logistic regression model. The data. Okay. There is a very nice R function which can do it. Give a name, the folder, call it as sepsis 1. The function is GLM. The R function is GLM, generalized linear model. And what is the response variable? Outcome. Tilde. What are the predictors? Dot. Dot means the predictors, the rest of the variables in the data. Technically, I'm supposed to type up. I should type up after tilde shock plus malnutrition plus alcoholism plus age plus infarction. I have to type it. I don't want to do it. You simply say dot comma. What are the predictors? The rest of them in the data. That's the meaning. I don't have to type every name. Identify the data. The data equal to sepsis. And most importantly, you need to type family equal to binomial. With the moment you say family equal to binomial, R will recognize this is a logistic regression problem. It will crank out the likelihood method or weighted regression, weighted regression approach. Okay, and will crank out the solution. Okay, important input is a family equal to binomial. Okay. So let us fit the model. Run it. Done. Okay. The process inside is numeric. It involves some iteration and the program is very efficient. Okay. And then you want to see the output. So you say simply say summary of sepsis 1. That's it. You get so much. GLM formula is equal to outcome tilde and the predictors, the rest of them in the data. Family is equal to binomial and data equal to sepsis. Okay. It talks about the deviance residuals and we got the estimates.
Bueno.
Hello? Any question? Okay. All right. Okay. You know, there's a lot of work, computational work behind. You don't have to worry about the computations. R does it for you. And the model is fitted. Okay. All right. And the thing is, you want to understand interpretation. Okay. Before that, I want to do something. Check goodness of it. Check goodness of it at the model. Because I want to know whether the fit is good. So that I can use, if the fit is good, I can use the model in practice. For example, in prediction. Okay. So goodness of fit. There is a little technical. Okay. The lower the residual deviance is okay. You can say the better the fit is. You know, at the bottom, you can see residual deviance 53.122 on 100 degrees of freedom. Originally, the data has 106 degrees of freedom, and we have estimated. Hello? Are you okay?
Yeah. Go ahead, Dr. Rao. It will meet.
Okay.
Everybody mute yourself. Everybody mute yourself if you are,
Okay.
are talking with other people.
Okay. And I'm trying to make it, I'm also teaching some statistics. Okay. The better the fit is. So what I do, when you talk about the fit, we talk about the null hypothesis. The null hypothesis, the response probability follows
ይቅርታ ማይካችሁን አንዴ ኦፍ ብታረጉት ሳይድ ቶክ ላይ
Okay, continue, Dr. Rao. Unmute yourself, Dr. Rao.
Is that okay now?
Yeah.
I'm muted all right from the beginning.
Not you're talking about your teaching some stat and maybe just a minute.
That's
or less.
okay. So it's what I call some minor aberration.
Yes.
Okay. So what we do, I'm trying to understand how well the model fits the data. So you postulate a null hypothesis. I'm optimistic. The response probability by the depth follows, okay, follows the logistic regression model pattern. Okay. And we need to calculate the p-value. Okay, this is a little technical. P chi-square, okay, and the residual deviance is 53.122. Degrees of freedom is 100, and the lower dot tail equal to false. Okay, so you need to calculate the p-value associated with the null hypothesis and click. Okay, and what do you get? The p-value equal to 0.99968 is much more than 0.05. And what it means is the fit is very, very good. It's an excellent fit. Okay, so you can say that the model is a very good summary of the data. Why do I say that? You have 106 observations in the data, and the model has only 6 parameters. The 6 parameters summarizing the entire 106 observations. Okay, and in fact, you might ask, you tell me the model. I can say the prediction equation. What is the model here? I can write it for you. The probability of a death after surgery. What are the chances of a death after surgery? Equal to exponential. Get used to that. What is the intercept? Minus, what is the estimate of intercept? Minus 9.75. That's my intercept. What is the estimate of beta 1? 3.67 times shock. And what is the estimate of beta 2? So we go to the next line. 1.21 times malnutrition. Okay, and what is the estimate of beta 3, beta 1, beta 2, beta 3, and 3.35 times alcoholism. Okay, and what is the estimate of beta 4? 0.09 times age. Plus, what is the estimate of beta 5? Correct it to 2 decimal places, 2.80 times infarction. Close it. Whole divided by 1 plus numerator. I'm going to want to type it again. That's the picture. Okay. We have a model in hand. I'm saying that is an excellent fit to the data. How do I use the model? I have a new patient. Gather information about the patient. Oh, all right. Okay. Okay. He's in shock. If he's in shock, put shock is equal to 1. If he's not in shock, put shock is equal to 0. Is he malnourished? If it is yes, put malnutrition equal to 1. If it is not, put malnutrition is equal to 0. Whatever information you have about the new patient, plug in the information into the model, you simplify it and calculate it, you will get the probability of it. That's how we use the model. Okay. And I want to talk about something. Okay. Tell us about the impact of each of the predictors on outcome. Once I'm happy with the model, I need to talk about it. What do you think? How much shock influences the outcome? How much malnutrition influences the outcome? You tell us the impact of each of the predictors and outcome. How do you answer that question? Okay. Let us talk about shock. Okay. What I do, I postulate a null hypothesis. What is the regression coefficient of shock in the original model? Beta 1. You go to the original model, population model. Every predictor has a regression coefficient. Shock has a regression coefficient beta 1. Alcoholism beta 3, and so on and so forth. I'm a skeptic. I'm a skeptic. I don't believe the shock has anything to do with outcome. Why do I say that? Let me go to my notes. You will see. Go back to the model. Look, this is my population model. Look at the population of all guys who went through the blood poisoning. Okay. If beta 1 equal to 0, it disappears. Okay. X1 disappears from the equation. And whatever may be the value of X1 has nothing to do with the probability of death. Whether X1 equal to 1, X1 equal to 0 is immaterial. The probability of death remains the same. We can say that if beta 1 equal to 0, X1 has no impact on the probability of death. Okay. It doesn't matter what the value of X1 is if beta 1 equal to 0. Okay. All right. You postulate the null hypothesis beta 1 equal to 0. Okay. And from the model, from the fit, okay, the estimate of beta 1 is 3.67. You know, I'm postulating, I'm speculating beta 1 equal to 0. X1 has nothing to do with the outcome, but I have only a sample. Okay. See, what is statistics about? Inference. What is inference? From population to sample. Okay. In the population, we speculate beta 1 equal to 0. I got a sample of 106 people. Using the sample, I estimate beta 1. It happens to be 3.61. Okay. I mean, people might say that. If the population beta 1 equal to 0, I would expect the sample beta 1 equal to 0. It's not going to happen. The sample is a microcosm of the population. Okay. In the population beta 1 equal to 0, you might get a sample with the beta 1 not equal to 0. That happens definitely. So the question is, okay, if the null hypothesis is true, okay, what are the chances of getting an estimate of beta 1 as large as 3, what did I say? 3.6. In the population, it beta 1 equal to 0. Okay. But in a sample, you get some number for beta 1 as an estimate. And what are the chances of getting such a estimate as large as that one? And the chances are p-value. And what is the p-value? 0.001610, and which is much, much less than 0.05. Okay. What you are saying is, if the null hypothesis were to be true, the chances of getting an estimate as large as 3.61 very, very low. But it happened. If the null hypothesis is true, such a number should not have arisen, should not have arisen. Okay, but it happened. So the assumption is wrong. So reject the null hypothesis. So p-value is very small, reject the null hypothesis. I can say that shock is very, very double star is a very, very significant predictor of outcome. I made such a statement before by doing a naive analysis. Okay, I studied shock and outcome in isolation. And I showed that, yes, shock is a very strongly associated with outcome. But this is that. Okay. And this judgment is better than the naive analysis so we have carried out before. Why do I say that? Why is it so better? Because the reason is all other predictors played a role. But I took everything into account, all other predictors together in the model. So The p-value I'm getting here is adjusted p-value. Adjusted p-value taking into account the presence of other predictors. That's why it is superior analysis. Okay. All right. Now we are ready. Okay. Let us look at malnutrition. Okay. Is it a significant predictor? Look at the p-value, 0.09, which is greater than 0.05. No. Is alcoholism a significant predictor? Yes. The p-value is very, very low. We can say that alcoholism is very, very significant. What about age? Yes, the p-value is very low. So I can say that age is very, very, very significant. What about infarction? Is significant. Okay. So what we learned from the model exercise? Alcoholism I can say is very, very significant. Okay. And I can say that age is very significant. Okay. And infarction is significant. Okay. So this is what you call your passing judgment on individual predictors, which are significant, which are not significant. The fit is excellent. The model fit is excellent. Okay. Now let me ask you one more thing. Of all the predictors, which one is the most significant? Okay. And I would say that alcoholism. Because why do I say that? Is the least p-value. The one with the least p-value is the most significant predictor of all this. You know, it makes sense. You talk to your surgeon about this, our data analysis, and he says that he's happy. Blood poisoning occurs typically from excessive drinking without control. The blood becomes poison. So the analysis came out very nice, and yeah, that's right. Alcoholism is the one that plays a big role. Okay. All right. So we did quite a few things now, and which predictor is significant, which is not. Okay. And later on, maybe I'll talk about a model selection. Can one tighten the model? I'll talk about it later. And then let me talk about what is called operation prediction. Okay. What does it mean? I have already put down the model. Okay, I have this model clearly spelled out. I got intercept estimate, estimate of beta 1, estimate of beta 2, and so on and so forth. They're all there. And what operation prediction means, I have a new patient. I might have even the same patients from the data. I have a new patient. I have all the information on the new patient. I know whether or not is in shock, whether or not is alcoholic, and so on. Using this information on the patient, can you estimate the probability of a death and consequently the probability of a survival? You say that is simple. You plug in the information into the prediction model, you should be able to calculate what is the probability of a death is. Sure. So simple. R can do it for you. You can ask R to calculate the probability of a death given that information. Okay. Let me demonstrate how to do it. We have two patients. Okay. With all the information and use the prediction equation to estimate the probability, estimate probability of death. Okay. And what you need to do is to create a data frame. With the information on the patients. Okay, I'll show you how to do it. Create a name, call it as a data. And talk about data.frame. Okay. Do you know information on shock? Yes. Both are in shock. 1, 1. I'm putting the two guys' data in the data frame. Okay. And do you have information on malnutrition? Yes. Both are undernourished. 1, 1. Do you have information on alcoholism? Do you have information on alcoholism? Yes. Both are alcoholic. And do you know their ages? Yes. One is 25 years old. The other one is 90 years old. And do you know anything about their infarction status? Okay. Yes. Both had infarction in the past. Close it, close it. I'm putting the information on both the guys in a single data frame. Okay. And you can run it. You can run it. It's there. And you can have a look at it. You can have a look at it. That's it. I'm giving you the profiles of two guys. Okay. All the two guys have bad habits. They were in shock, undernourished, alcoholic, had infarction. One is a pretty young guy, another one is a very old guy. So using this information, using the prediction equation, I want to estimate the probability of a death. Can you do it? Sure. Ask R to do it. All right. So give a name. What name shall I give? Okay, let me see. Call it as MB1. Call it as MB1. The R function is predict, is an R function. What is the output called? Okay. Sepsis 1. Sepsis 1 is the output folder. Okay. Sepsis 1 is the output folder of the logistic regression. And the new data equal to this data I have. And what type of result you want? And type is equal to double quotes. I want a response probability. You have to tell R what you want. And let me run it. Done. Okay, it's calculated. You want to look at MB1. Okay. The first guy, the probability of death after surgery is 97%. The second guy, the probability of death almost 100%. Okay. They're talking about a 97% and versus 100%. Because both of them have bad habits. One is young, did not help him that much. He has an advantage of only 3 percentage points. One is old and he's going definitely, almost surely will meet his maker. Okay. You know, I can do one thing. Okay, look at the data here. I modify the data. Edit, copy. I modify the data. Edit, paste. Okay. Call it a new data as a data 1. Are they in shock? Both are good guys, not in shock. Okay. Are they undernourished? No. Both of them, no. Are they alcoholic? Both of them, no. 0, 0. And what about their ages? One is young, the other one is old. Did they have infarction in the past? No. Both of them, no. I'm changing the profiles. So let me run this data 1. Okay. It's done now. So what I look at is data 1. Show me the data. Guy 1, 0, 0, 0, 25, 0. Guy 2, 0, 0, 0, 90, 0. All of them have good habits. One is young and one is old. Can you do the prediction? Yes, why not? So let us do. Okay. Copy MB1. Okay. And paste it. Call it as a new folder, MB2. Predict sepsis 1. New data equal to data 1. And the type is equal to response. Okay. and run it. No problem. So let us look at the output MB2. Look at the output MB2. Look at the first guy. Clean habits. Young. What are the chances of death? 0.0006. Look at the second guy. Clean habits, but old. What are the chances of death? Hello? Okay. What are the chances of death? 18.8%. So there's a big gap. You can see, and the age is playing a role. Age is playing a role, right? So virtually a difference of 18%. Okay, all right. And what I want to do, let me go back to my notes. I think I fairly gave you a good introduction to logistic regression, what the model is, and fitting the model to the data. And then I checked the goodness of it. I examined the significance or non-significance of each of the predictors. I showed you how to do prediction. Okay. There are a lot more things that can be done with the model. And, so what do you call misclassification rate, all those things that can be done. And also, out of this model, there are a number of things. Okay. Flow from the model. Okay. One of the things is, can one develop a biomarker from the model? Okay. And another interesting thing is, we are estimating probability of death or survival. It is estimating probability of death. This is what I call soft prediction. This is what is called a soft prediction. Okay. Can you predict directly whether one dies after surgery? Whether one dies, can you predict directly whether one dies after surgery? I don't want probability. You tell me, you're going to die or not? That's all I want to know. Okay. I want to know whether you can do it or not, whether one dies after surgery. And this is so-called hard prediction. I'll show you how to do it. Okay. And another important thing is, can one present the fitted model graphically. Because typically editors love it. Okay. Look at the prediction equation, looks pretty complicated. Can you interpret the model graphically? Usually not possible. How can I present it graphically? Okay. And in this case, it is doable. Because you know why? 4 predictors are binary. Yes, we know that. And one predictor is a numeric. This is giving me an idea. What I can do is take x is equal to x variable as age. Okay. And the y variable equal to probability of death. Okay, all right. So for each choice, of the other predictors, graph the probability of a death as a function of age. I did this, it took me a couple of hours to get the graph, but I want to show you what I did. If you can do something like this, is a crowning achievement. So let me go back to my notes. Basically, I eliminated malnutrition model a little tighter. Chuck out malnutrition from the model. Refitting gives the following estimates. Okay. All right. Okay. So I did this one. Okay. And there are other examples. I would like to talk about it later. Model fitting using R, another example. Okay. And because there's so many examples. Okay. So these examples you can read at leisure. And I talked about the goodness of fit, all those things. And this one. Let us go back to sepsis data. Okay. And refit it. Look, this is the model. And these are the regression coefficient. We have already seen it. And then the prediction I talked about. I talked about 2 guys. I talked about one is 30 years old, 60 years old. I did the prediction. And the first guy, the chances of death 5%. And the second guy, the chances of death is 45%. There is a difference. both are not in shock, both are undernourished, both are not alcoholic, both had infarction, but one is young, 30 years of age, one is middle age, 60 years of age. Does it make a difference? They have identical profiles except for age. Will it make a difference? Yes, sir. For the first guy, the chances of death is 5%. And the second guy, the chances of death is 45%. Age. Chances of death for the younger fellow, 5%, and the older one is 45%. Age is playing a big role. Okay. And I did this one prediction for all. I'll come to that little later. I don't know whether I did a graphics, model based odds ratio. That's another big thing I need to do. Okay. And goodness of it, okay, graphics. A type model. Remove malnutrition. I did that. It's gone because it's not significant. I took the liberty of checking it out. Okay. All covariates are significant. How do we present a logistic regression model? Okay. And what I did, the probability of death is my Y. Okay. And the age is my X. Age is my X. Okay. So what I did, I looked at several possibilities. Shock is equal to 1, alcoholism equal to 1, infarction is equal to 1. Okay. Draw the function probability of a death as a function of age. I use the curve function. Anyway, to make things, this is the graph I got. Okay. X-axis is age. Y-axis is the probable scenarios. You look at the red curve. Shock is equal to yes. Alcoholism is equal to yes. Infarction is equal to yes. What are the chances of death? And my x-axis is age, ranging from 20 years to 90 years, 20 years to 100 years. So what do I find? If you all have the bad habits, shock, yes, alcoholism, yes, and infarction is equal to yes, even if you are young, it's not an advantage. The chances of death after surgery is over 80%. And as age increases, the chances are all hitting 100%. And on the other hand, other extreme, shock is equal to no, alcoholism equal to no, and infarction is equal to no. The clean guy. And what are the chances of death after surgery? If you are a pretty young guy, probability of death is almost 0. As age increases, the chances of death are rising, and it doesn't go beyond 40%. If you all have a good habits, even if you are 90 years old, the chances of death doesn't go beyond 40%. You can survive with a 60% probability. So this is the message I'm sending. And all other cases intermediate. Okay. And the next best thing is shock is equal to no, alcoholism equal to no, and infarction is equal to yes. Okay. And starting from 20 years of age, going up to 90 years of age, what happens to the probability of a death? Is pretty low at a younger ages and start rising very steeply. When it comes to 80 years of age, the chances of death over 70%. And if it comes to 90 years of age, the shock is 80%. chances of death are 8. This is a summary of our model fitting exercise in a nutshell. This kind of a graph may not be possible. In this case, it is okay. We have only one numeric variable, rest of them are all binary. I could do this one. Okay. All right. Okay. And it took quite a while for me to create such a graph. I give the code is there in my notes. Okay. So what I can say is graph is done. Okay. And let me talk about what is called hard prediction. What is the philosophy? No probability. I don't want a probability. I'm allergic. Okay. And predict directly death or survival. Okay. How do I do that? Right. I can say it's a very simple thing. Predict death if the probability of death from the model is greater than 50%. Okay. And predict survival if probability of death less than or equal to 50%. A simple convention. So I have got my model, and the new guy comes along. I have the information on all the predictors. I can estimate probability of a death. If the probability of a death is greater than 50%, yeah, my hard prediction is a death. If it is less than or equal to 50%, my prediction is survival. This is how I answer the question. Okay. So what I do for this, I need to calculate the probability of death for everyone in the data. Okay. So what I do, maybe open a folder, prediction. Let me say soft. Our function is to predict. The output folder is sepsis1, and the new data equal to, okay, new data equal to sepsis. I'm using everybody in the sepsis data, and type is equal to response. This I call it a soft prediction, okay, as opposed to hard prediction. And run it. Done. We have 106 predictions. We have 106 predictions, okay. And if you want, you can look at the top 6 predictions, head of soft. Show me the top 6 predictions corresponding to the top 6 people. The first guy, the chances of death is 1%. The second guy is about 8%. The third guy is 1.5%. And the fourth guy is almost 0%, and so on and so forth. Okay. All right. I want to do hard prediction. What I want to do basically, if the probability of death is less than, greater than 50%, call it as death. If the probability of death is less than or equal to 50%, call it as survival. Okay. So you need to replace the numbers by words. Okay. Replace the numbers by words. So I use the command if else. Okay. You say that if soft greater than 0.5, if soft is less, it's greater than, I'm sorry, is greater than 0.5, call that phenomena as a death. If it is less than or equal, if else, if this is not true, call it as survival. Very simple command. Take a number. You replace the number by words. Okay. So let me make it is just 1 minute. I don't know, maybe it should be okay. Let me try. Okay. And look at, you will have 106 predictions. We have 106 predictions. And then you can look at the head. Give me the top 6 predictions. Head hard. Run it. It's clear. The first guy, the chances of death 1%. So survival according to our convention. The second guy, probability of death is 8%. So it is survival according to our definition. The third guy, survival. The fourth guy, survival. The fifth guy, survival. The sixth guy, survival. Okay. All right. All right. So the next question is, we are making hard predictions for everyone in the data. We are saying as per the model. Don't forget that. Using the model. However, we know the truth. However, we know the truth. Whether he died or survived, you know, from the data outcome. You match them. Okay. Check how well the prediction went on. Okay. So create a folder. Goodness of prediction. Create a data frame. There's an R function. Observed. Okay. And you go to sepsis. Dollar outcome. The outcome column gives you what happened in reality to the fellow. From the outcome column tells you we know the truth, whether the guy died, whether they survived after surgery. And using the prediction model, we are predicting whether he will die or survive. So observed is equal to identify the outcome. Okay. And the predicted equal to hard. Predicted is equal to hard. And run it. Oh, data frame. Data frame is there. Data dot frame. Okay. Let me see. Yeah, I don't know. It's not recording it. Okay, let me run it again. That's okay. Okay, just to look at it. Goodness. Look at the entire folder. Run it. Understand now. Look at a guy number 1 in my study. What was observed? He survived. Okay. What is predicted using the model? Survival. Aha, the model did a good job. Look at the number 2 guy. What happened in reality? He survived. What does the model say? Survival. Aha, the model did a good job. What about number 3? Good. Number 4, good prediction. Number 5, good prediction. Number 6, in reality, he died. But the model says survival. Ah, that's a mistake. The model did a bad job. What about number 7? Good. A good prediction. Number 8. Okay. And a bad prediction. Number 9, good prediction. Number 10, good prediction. Number 11, good prediction. Okay. You see, I'm trying to compare the reality with what the model does. So, find the total number of bad predictions. And I'm telling you guys, it's a cross tabulation. Cross tabulation, you look at goodness dollar observed, comma, both are binary. Observed is binary, predicted is also binary. Goodness, dollar, predicted. Cross tabulation. Observed is a binary, predicted is a binary. How many zero survival? How many zero death? How many one survival? How many one death? Okay. Cross tabulation. I would like to give a name, some MB3, some name. Give a name and run it. Got it. I got it. Okay. And look at this 2 by 2 table, MB3. The rows, reality. The columns, hard prediction. You know, in reality, zero means survival. There were 84 people who survived in reality. What did the model say? Aha, it predicted out of 85 survived in reality, it predicted one guy died and the remaining 84 survived. Therefore, one mistake. There are 21 people who died in reality. What did the model say? 13 died. Goody goody. 8 survived. Bad. So those 8 are bad predictions. Misclassification rate. Nine divided by 106. And what is the misclassification rate? What is the misclassification rate? 8%. How well? I did a goodness of fit. I got a very, very high p-value. And I converted a soft prediction into hard prediction using a very simple convention, 50% cutoff threshold. And if you use a hard prediction and the model committed mistakes 8% of the time. It's good. It's not bad at all. Okay. So I covered quite a bit of a ground. There are other things to be done. Okay. One is what do you call model selection. The other one is cross validation. Model selection means do we need all these predictors for prediction? Maybe a small number of predictors could do as good a job as a whole set of predictors. Cross validation means, you know, you are you use the entire data to get the prediction model. Okay. and you're using the entire data to check on calculate the misclassification rate. We don't like that. You be the judge and you be the jury. So what they're asking is, you fitted a model. If you have some other data coming from some other source, apply the model and do prediction and see how well you are doing. You can't do that. It's difficult to get data from other sources. Can you do some kind of a cross validation? It simply means use the, for example, select 70% of the data randomly, fit the model, and use the model on the remaining 30% of the data and check the misclassification. That's what is cross validation. So these two things are pending. Hopefully, I'll try to get to them. Today, I started a bit ambitiously. I want to do so many things, and the time is not enough. It is 8:52 now. I think I'll stop and I'll take questions from the participants. Go ahead, guys.
Very good. Thank you so much, Dr. Rao. It's
Wow.
amazing all these things you do in so long time, just 3 hours. So thank you very much again.
Okay.
Is there any question for the attendee? You can unmute or put it in the chat box.
Yeah, sure.
So as Dr. Rao mentioned, he start from simple and he's progressing to a more advanced every day. You remember from yesterday, today he has more complicated. Tomorrow is more model selection and cross validation, which is more important.
It's going to
maybe
more tough, I'm telling you.
Yeah. So on Friday, he's going to move on to the big data. Now we have this small Excel type. Now you may not see all the data. What happened? How do you really figure out data in the cloud or somewhere which you can see all of the data? So
sure.
He's moving to the progressing to a more advanced level. So if you have question, please speak out now.
Yeah. The thing is, these are all some of the basic techniques. Whether you have a small data or a big data, you can apply them.
Yeah.
Okay. You need to understand what goes on inside. What are the important concepts? You look at a logistic regression, there's so many things coming out of it. Okay. We started small, we did some naive analysis, and I wrote the model. Is a tough thing to write the model and fitting the model, goodness of it, and the significance of the predictors. So many things we did. The soft prediction, hard prediction, and graphics. Okay. So if you can master whatever is done today, I mean, I have other examples in the notes. Okay. You can practice. You can practice other examples in the same kind of a style, and then you can get a good grip on logistic regression.
I think that's a good thing. Follow the examples and run by yourself and see whether you get the same result and expand it.
Yeah.
And how do they get data set from the R? They
download the data. For example, I have Excel data. Copy the data to clipboard.
Is there a data set from the R studios they can access pre-existing data?
R studio also same idea. If it is in Excel, it's very simple to do it. Copy the data. If you are in Windows, copy the data to clipboard. Okay, and then right at the top, read.dlim. That's an R function. Whatever is a copy to the clipboard, bring it on to R console.
Very good.
Yeah, that's the one. In fact, you may have a data as a text file, for example. You may have data as a CSV file. CSV is the same as Excel. You may have a data in SAS format, and for each, what R does, wherever you have the data, in whatever format you have the data, you can bring it into R.
Very
And
good.
you know, go to internet, you just simply type in Google, importing data into R. It gives you instructions. How
Very
to do
good.
it.
Is there any question? Otherwise, we stop today's session at this time. There's already time, 2 minutes left, and we'll continue tomorrow in a more advanced, more interesting topic. So thank you everyone for sticking for these long hours, and I'll see you tomorrow.
Okay, thank you, Tasfaye.
Yeah.
Enjoyed it.
Sure.
Thank you very much.
Thank you. Thank
Thank
you.
you very much.
Thank you,
Yeah,
Professor.
for attending. Yeah. So
Thank
the
you for
only
attending.
piece of advice is practice, practice, practice. That's all I
Yes.
can say.
Yeah.
Okay. All right.
Thank you, Dr. Rao.
Thank you.
See you later.
Bye.
Thank
Bye.
you.
Bye.
Thank you. Thank you.
Do they expect not, Dr. Rao? He may not, he may left already, but we'll share you the notes at some point later in the evening. So we'll send you in the morning at your time. All right, thank you again.
Please once, can you listen me?
Yeah,
If possible, it's best to send the R command with the handouts. Yes, and sometimes we can display the outputs. And then,
there's no other command. I thought in the handout, there's R command as well.
okay.
You may double check. I'll check with Dr. Rao, but I thought there is some of the steps you can even copy and paste there.
Good. Okay. Yeah.
All right. Okay. Bye.
Hi,
Everybody.
Dr. Rao.
Yeah.
Sorry, do you expect handout for tomorrow?
I can send you a new one.
Okay.
But the question is what I should cover. I did not complete whatever I planned to do today. I did not talk about a multinomial regression. I did not talk about ordinal regression. Should I continue on those two topics?
Hello.
Yeah. Yes.
Please add my email to your contact and share the materials.
Said Dr. Rao.
Grants.
Sorry, you are muted, Dr. Rao.
Oh, yeah, I can hear you.
Go ahead. So probably if you feel what's left from today is important, you can start from what you want to cover from today, but you can also touch what's coming up with the model selection and other things.
Yeah, model selection is also important. Cross-validation is important.
Yeah.
Okay. So what I do, there are two critical things, multinomial regression and ordinal regression. They're very much used in big data and also in genetic studies. Okay. So I'll start on those two and then go sail into model selection.
Yeah, that would be good. That would be good.
Okay.
All right. Thanks so much.
Right. Bye.
Bye.